This is page 7 of our Unit 2 packet. So on page 6, we had just been looking at some of these patterns for electron configurations, which is essentially giving an address to where electrons live. And we had left off by saying that when we write these configurations, the number in front is our energy level, which tells us which ring, how far away from the nucleus the electrons are. The letter tells us what the shape that these electrons are moving in looks like. And then the exponent tells us the number of electrons that are moving in that type of orbital. So on page 7, I'm going to write basically the same thing again. This number is called N, which is our energy level. Okay, so again, that tells us how far away from the nucleus the electrons are located. In this case, ring number 1. S tells us the shape. So are the electrons moving in an S shape, which is spherical, or the P shape, which is the dumbbell shape? And then the exponent is the number of electrons in the sublevel. And in that sublevel just means in that type of shape. So in this case, there are 2 electrons in that spherical shaped orbital. When we look at this little periodic table, I'm just going to color code this with kind of the rules and the patterns that we already saw. So I'm just going to grab a couple of different colored pencils to use. Hopefully I'll pick some that have some good contrast. All right. So the first thing, if we're just going to group these by letter, we said that everything in this section of the periodic table, the letter that we saw when we filled these in before was S. This is called the S block. Make that a little darker. There was one other element that's also in the S block, which was this one over here. In a lot of ways, helium really should kind of be right here in that blank. Okay, so that was our S block. The next letter that we saw when we were filling in those patterns was P. So our P block is over here on the right side. And these are called blocks because when I draw them, they're actually going to be squares or rectangles. So this over here is our P block. The next letter that we saw was D. And D was this middle section over here. So that's our D block. And just as a note, there's this asterisk and the double asterisk. These 2 elements right here, lanthanum and actinum, these 2 belong right here. This is just as a note to remind you like, oh wait, the periodic table should be broken and then continue down at the bottom. So that's why those stars are there to remind you to go through that bottom row. Our last block, which is this section of the periodic table, this was given the letter F for the shape that these electrons occupy in their orbitals. F. So that was how we knew which letter we were going to write in our pattern. The number in front comes from the row number, which is right here, which we call N. So if I wanted to know what number to write in front of hydrogen, I would write 1, or what number in front of lithium's electron, I would write 2. So this would just be an N that's going to go in front of S. So whatever number that is, that's the same thing that we did for P. So we started here with P, and that was 2P1, 2P2, 2P3. But for D and F, there's something a little bit different that happened. When we were over here in 4S, when we went to D, it was 3D. So whatever row number it's in, like row 4, I actually have to subtract 1 to know the number that should go in front of D. So here I'm in row 4, so this would be 3D. Here I'm in row 7, so this would be 6D. From there, we were in row 7 for S, and then 6 for D, And then when we continued on down here, we're actually one lower than that. So we were in 5 for F at the very bottom. So if we look at which row this would have been in with the 2 stars, that would have been in row 7, but it becomes 5F. What we're really going to do is take that row number and subtract 2 to figure out the number that goes in front of F. So when we look at the periodic table and we think about these patterns, we can actually write in order that we see these different orbitals appear in. At the beginning, I start with 1s, that's the first one. And then the next that I encounter is 2s here. Then row 2p would come next. Then 3s would be here. Row 3p would be next. So I'm just reading the periodic table like a book, top to bottom, left to right, and listing out the order of these. Next would be 4s. And then next, I'm in row 4, but I have to subtract 1, so 3d would come next. And then after that, I go back to my normal counting, so I'm in 4p. Over here is 5s. 5 minus 1 is 4d. Back to just regular, so 5p. And we can continue across the whole periodic table getting this order. This is written, when we read the periodic table from top to bottom, left to right, from the lowest energy orbital, closest to the nucleus, getting higher and higher and higher in energy as we move farther out. Okay. This order that we just looked at is called the Aufbau principle. The Aufbau principle says an electron occupies the lowest energy orbital available, and that order comes from that periodic table pattern that we saw. So in order of increasing energy, if I listed them all out, it would be what we see down below, which really, again, just comes from reading it from the periodic table. This isn't in order to memorize, it's in order to know the pattern of, and then you just read it across. All right. The other 2 pieces of this come down to what are going to be called orbital notations. So we're going to practice those, but we're going to hold off on that for just a little bit because we want to practice electron configurations a little more before we get into orbital notation. Okay. So let's do a practice first of writing out some electron configurations, and we see some examples of that on the next page. So we're going to go ahead and flip over to page 8. All right, so I'm going to pick an element from the periodic table. Let's start, for example, number 1, how about with sodium? Okay, so sodium is Na. So the very first thing that we want to do is just know how many electrons does sodium have. Sodium has 11 for its atomic number, which tells me it has 11 electrons as well. If we wanted to figure out how we would express all of these electrons, we could write what's called the electron configuration, which is where I am going to be reading the periodic table like it's a book from top to bottom and filling in those electrons until I get to sodium. So in order to get to sodium, I have to read through the rest of the periodic table. I'm going to start up at the top. When I'm starting at the top of the periodic table, I'm in row 1. So the first part of my configuration would be 1. And this block that we're in over here is S. So that's my letter. And then I'm going to count across the whole block until I get to the end. So 1, 2, remember that helium's still part of the S block. So the first 2 electrons for sodium are in the first energy level. They're in an S-shaped orbital, and there's 2 of them in there. I've just accounted for the first 2 electrons out of the 11. Notice that I didn't have to write 1s1, 1s2, because if I'm saying there's 2 electrons there, when I say 1s2, I've said there's 2 electrons there. I don't need to say 1s1, because that means there's only 1 electron, but there's really 2. All right, continuing on to our next part. So now I'm in row 2. This is the S block, and I count across 1, 2. So by the next part, I'm in row 2 in the S block, and I counted across the whole block. So 1, 2 to get to the end there. Next, I'm still in row 2, but over here I've changed the letters now. Now I'm in the P block. So this is row 2, but P block, and I'm going to count across 1, 2, 3, 4, 5, 6 to get all the way to the end. Okay, so 2 for the row. P-shaped orbitals are holding 6 electrons. Okay. I'm almost to sodium. Sodium just is one more box. So now I'm in row number 3. This is the S block. And I just count until I get to sodium. I don't want to pass it because I'm just trying to get to sodium. So 3S, and then I'm in the first box, so 3S1. So this is called an electron configuration. We just wrote where all of the electrons are located. And notice for this that we said 2 electrons are located here, 2 are located here, 6 are located here, and 1 is located here. If we add those up, 2 plus 2 plus 6 plus 1, 2 plus 2 is 4, plus 6 is 10, plus 1 is 11. We just said there's 11 electrons, and that's exactly what we said at the beginning. Sodium has 11 electrons, and we just wrote the address for each of the electrons. Okay. All right, if we were going to look at another example of this, let's do chlorine this time. So chlorine is here, atomic number is 17, so it has 17 electrons. Okay. So when we go down to do the electron configuration, we're going to be reading across the periodic table from top to bottom, left to right, until we get to chlorine. Okay. So to get here at the beginning, let's see if I can have the paper so we can see both of these things at the same time. All right, so at the very beginning, we're here in row number 1, and this is the S block. So 1S, and I count across, 1, 2. All right, next I'm in row 2. This is the S block, and I'm going to count across, 1, 2. I'm still in row number 2, so that number doesn't change. But when I go over to this section now, I'm in the P block, so my letter changes to P, and I'm going to count across. 1, 2, 3, 4, 5, 6. That's telling me 6 electrons live in the second energy level in those P-shaped orbitals. Next, I'm in row 3. The letter for this section is S, and I count across. 1, 2, until I get to the end of the S block. I'm almost to chlorine, right? Chlorine's right here. So I'm still in row number 3. Now I'm in the P block. I changed the letter, and I have to count until I get to chlorine, and then I'm going to stop. So 1, 2, 3, 4, 5 to get to chlorine. Again, from here, if we look, we said 2 electrons live here, and 2, and 6, and 2, and 5. So we've identified all these different electrons being in different places. And so 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, and plus 5 would get us 17. And that's exactly how many electrons we said that chlorine has, 17 electrons total. So these electron configurations, again, are a way of identifying where these electrons live, so to speak. When we drew our Bohr model of the atom, if sodium was located in the 3rd ring, we would have said that means if sodium is located in the 3rd row, that means it has 3 rings. How many electrons should have been in the 1st ring? 2. So we would have drawn those on here. How many should have been in the 2nd ring? Well, there's 2 and 6 is 8. So 1, 2, 3, 4, 5, 6, 7, 8. And how many should have been in the 3rd ring? 1. This is our Bohr model. It tells us how many electrons live in each ring, but the electron configuration tells us specifically, well, what types of shapes are they occupying, because they're not all moving in circles. Okay, so that's kind of how the Bohr model and electron configurations relate to each other. All right, let's take a look at what's called noble gas notation next. So noble gas configuration or noble gas notation. So this isn't really a review because we haven't seen this yet. Noble gases are the name for one periodic table family, one group, which is all the elements in group 18. So all the elements that are located right here in this column are called noble gases. So group number 18, which is the far right column. All elements are trying to become like noble gases, so they're a significant family, and we'll talk more about that next unit. But what they have that's special is they have their outer shell of electrons completely filled. When we get to the end over here, this is where we see that we've reached like the filled P block, and the S block we already filled over here. So this is where we finished filling up one energy level, and then we're about to start a new energy level. So for example, if we were going to write the electron configuration for neon, neon is here. We would start up at the top. We are in row 1 in the S section, and I count across 1, 2. Next would be row 2 in the S block. So 2S, count across 1, 2. Still in row 2, but now we've changed to this pinkish color, which is our P block, and I count across till I get to neon. 1, 2, 3, 4, 5, 6. Okay. So notice that we've filled up the P. We've maxed out the P orbitals. They can hold 6 electrons total, and we've filled that, and we're about to, if we continued on, start row number 3. So that's kind of the significance of noble gases. Okay. What we can do is we can use noble gas notation as a shortcut to write longer electron configurations. We can say, what if you started at this noble gas, and then you just need to add on extra electrons? So for example, we don't have an example here that we're actually trying. Okay, so let's do one that would be really hard. Let's look at francium. Francium is down here. Francium has a lot of electrons. If I look at the periodic table, it's element number 87. I don't want to write an electron configuration for something that has 87 electrons. That's going to take forever. So the shortcut method is, first thing we're going to do is find the closest noble gas with fewer electrons. So that means I'm going to start at this element, and I'm going to go backwards on the periodic table until I run into something that's in this column. So if francium's here in row 7, I'm going to go backwards, and the previous element before francium that's in group 18 is radon, which is Rn. So I'd write its symbol in brackets. And then what we're going to do is we're going to just tack on extra electrons. We're saying, okay, it's like radon, which is element number 86. It has 1 extra electron. Where's that 1 extra electron located? And we're going to write that as this next piece. So the only electron now that I need to identify for francium, instead of all of them, is just the 1 electron that ends us here, which would be the electron that's in the 7th row. It is in the S block, and it's the first element here, so there's only 1 electron in that S block. So instead of having to write 1s2, 2s2, 2p6, 3s2, 3p6, and keep going all the way down the periodic table, I got to use this shortcut. It's like radon with an extra 1 electron in the 7s orbital. Okay, so that makes it really much quicker than what we were doing otherwise. Noble gas configuration for sodium. We'll end up putting this on the next page because I use sodium as my example there too. So for sodium, sodium is here. So I'm going to go backwards. So I'm in row 3, so I'm going to go backwards to row 2. Neon is the last noble gas that we had passed. So now I just need to say how much farther is sodium past neon. Well, sodium is in row number 3. It is in this section that we call the S block, and it is in the first box in this section. So sodium is like neon with an extra electron in the 3s orbital. Okay. If we continued and we looked at aluminum, aluminum is here. So I'm going to go backwards on the periodic table. That was row 3, so I'm going back to the end of row 2 to get to neon. So aluminum and sodium both are closest to neon. And then if I say aluminum's like neon, but I have to add some extra electrons, well, what electrons do I add to get here? This is row number 3, so 3s and 1, 2. And then I'm still in row 3, but now I'm in the P block, the pink section, and I'm in the first box, so 3p1. So our noble gas notation just makes it so that we don't have to write the whole beginning. I just say it's like a noble gas and then add on the extra electrons. I'm going to go ahead and transfer this to the next page where we had our sodium example. So this is the one we just did. That was supposed to be a 3s1 for sodium. Okay. Our other example on this page was for chlorine. So if we look at chlorine and we wanted to figure out what noble gas we already passed to get to chlorine, I'm going to go backwards, 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 and then back. It's still neon for this one. So from neon to get to chlorine, what did I have to add? I needed to add these electrons in the third row. 3s1, 2. Still in row number 3, but now I'm in the P block. 1, 2, 3, 4, 5. Okay, so what we'd add on here was the 3s2 and the 3p5. So I'm really just adding on these sections because by writing neon, I've already accounted for this first section. I've already accounted for the whole first row and the whole second row by saying neon, and then now I just need to add on the third row electrons. All right. Last piece on here is looking at orbital notation and orbital diagrams. So we just need to know one more thing first. Well, two more things. When we are drawing electron configurations, instead of writing them out with numbers and letters, we draw them with arrows. And so if I'm saying that there are ever 2 electrons in the same orbital, like when I say 1s2, there's 2 electrons in the s orbital, they must have what are called different spins. And what that really means is that the 2 electrons are moving independently of each other, and it was typically thought of as kind of being like one's moving clockwise and the other's moving counterclockwise, which isn't exactly true, but that's kind of where that started from. So the way that we draw electrons is electrons are going to be drawn as arrows. So an arrow is an electron, and I need to show them having different spins, which really just means I need to draw my electrons pointing in opposite directions. So if I'm going to draw 2 electrons living in this same room, so to speak, one has to be up and one has to be down. Kind of like saying the 2 electrons are living in bunk beds. One person's on the top bunk, the other person's on the bottom bunk. All right, when we get to some of the sublevels, like p orbitals, for p orbitals, there are 3 different p orbitals. There's the p orbital that's up and down, there's the p orbital that's left and right, and there's the p orbital that sticks out of the page. So 3 different p orbitals, and there's allowed to be 2 electrons that are in each orbital. So for p orbitals, since there's 3 of them, 2 electrons can go in each. That gives us a total of 6 electrons possible in the p orbitals. When I'm trying to draw electrons filling these different orbitals, this is called Hund's rule, and this says orbitals of equal energy are each filled with 1 electron before any are paired. I always call this kind of the law of going into a movie theater or an auditorium where you don't know other people. If there's only 10 people in a movie theater and you don't know anybody, you're going to sit away from other people. You're not going to go and sit right next to somebody you don't know when there's 100 other empty seats. Electrons are kind of the same. They're going to space out as much as they can before somebody else sits in the seat right next to them. So if we have 3 electrons to fill in, I would put 1 in this box, and then the second electron is going to go into a different box, and it's going to point the same direction, also up. And then if I have a third electron, it's going to go in the third box, also up. Notice that they've spread out, 1, 1, 1. Nobody's paired up yet. If I have a 4th electron, now I'm going to go back to the first box, and it has to point down, but now I actually have a box that's partnered up because everybody's spaced out equally. Now somebody has to sit next to somebody. There's no more, big open gaps that it can take. So this is called Hund's rule. I just noticed I didn't fill in these group. Are these numbers across the top? And period are these numbers going down. So period is row numbers and group is column numbers. I'm just going to fill those in. All right, well, let's go ahead and flip over. We have 2 examples to look at real quickly. Then we'll be done with page 7 and 8. Okay, so for sodium, the orbital diagram, again, is the way that we draw electron configurations with arrows. So with orbital diagrams, we're going to start at the bottom, the lowest energy level, and then we'll fill them going up, 1s, then 2s, then 2p, then 3s. So it's the same thing that we already saw for the order. Okay. If I look down at my electron configuration down here, in the 1s orbital, I should draw 2 electrons. And our rules that we just looked at said we're going to point them in opposite directions, 1 up, 1 down. Okay. Next, in the 2s orbital, I should have 2 electrons, 1 up, 1 down. Okay. Next is 2p, and in the 2p orbitals, I should have 6 electrons total. So I'm going to draw 1 going up, 2 going up, 3 going up, then I can start drawing them down. So number 4 is down, number 5 is down, number 6 is down. 3s, I should have 1 electron. I'm always going to draw them up before down. So that would be our orbital diagram. Orbital notation is really the same thing. We just draw it left to right instead of up and down, which really just saves us space. So this 1s orbital, I would just draw it as a line instead of a box just to save time. 2s would go here. The 2p orbitals, I need to draw 3 of them because there's 3 2p orbitals. And then 3s gets a line. So it's the same thing we see up here. And then I'm just going to fill in the exact same arrows. So 2 on this one, 2 on this one. These ones each have 2. And then 3s was 1. So again, orbital notation, orbital diagrams, really the same thing, except drawing them left to right versus up and down. All right, so last example for chlorine. If we look at what we already wrote out for the electron configuration, we're just using this to fill in our orbital diagram. So in the 1s orbital, I had that filled, 2 electrons. In 2s, we had 2 electrons. In 2p, we have 6, so 1, 2, 3, 4, 5, 6. In 3s, I have 2 electrons. And then in 3p, there's 5, so 1, 2, 3, 4, 5, and we would end there. Okay. So these, again, are just different ways of representing where electrons are located and what they're doing. Orbital notation, in that 1s box, I drew 2 arrows. In the 2s box, I drew 2 arrows. In the 2p section, there was 3 boxes, so there's 3 lines. Each line got 2 arrows. This goes back to what we said before. A single orbital can never have more than 2 electrons, so that's why there's 3 different lines and each one has 2. I don't draw one line with 6 arrows on it. 3s has 2 electrons, and 3p has 5. So this is how we can express where the electrons live with electron configurations, noble gas configurations, and orbital diagrams and orbital notations. So lots of different ways of showing where the electrons are located in these atoms.